This is my geometry course. Today we're going to prepare for test number 5. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. I've said it before, I'll say it again. I know I sound like a broken record, but I need to remind you that you cannot pass a math exam without doing at least 2 days of studying. And in order to force you to do at least some studying, we're going to do a practice test right now together, and I'm going to give you a practice test for homework. These practice tests are not optional. They are mandatory. Do not take the test in the next class without doing these 2 practice tests. So let's get into it. As usual, 25 problems, 4 points each for a total of 100 points. You're allowed to use a calculator on this test. And whenever you need to use pi, be sure to use the pi button on your calculator. That's very important. You must use the pi button on your calculator whenever pi is required, or else your answer may not be accurate. Also, graphing paper might be useful for some parts of this test. So if you do have graphing paper, that's preferred. So, as usual, I want you to try these problems on this practice test before you just watch me do it. I want you to think about the problem. I want you to think what it's asking you and attempt the problem yourself. If you get stuck, that's okay, but give each problem an honest attempt. And that way your mind is going to be much more engaged. You're going to learn much more as we take this test, rather than just, again, watching me do every problem. Watching me do each problem is really not going to do much to help you. You have to engage your mind. So go ahead and try problem number 1, and when you come back, we'll do it together. All right, we're back. In this problem, we need to use the equidistant chords theorem. So equidistant means that these segments here are congruent. They have equal length. So these chords are the same distance from the center of the circle. And by the way, we know they're equal length, obviously, because of the purple tick mark there. So what the theorem tells us, the equidistant chords theorem, it tells us that these chords must be congruent. So 2y minus 1 must be equal to y plus 8. Subtract y from both sides, add 1 to both sides, and we get y is equal to 9. So that was a pretty easy problem. If you got that one right, good job. Go ahead and try number 2, and when you come back, we'll do it together. All right, we're back. In this problem, we need to use the segment lengths of intersecting chords theorem. And that tells us that if you have 2 chords in a circle that intersect, then the segments that are created are related in this way. This segment times this segment is equal to this segment times this segment. That's just something you're going to have to memorize. So 7 times 11 is 77, and dividing both sides by 10, we get 7.7. So if you got that one right, good job. All right, let's do number 3. It says, if K is the centers of the following circles, find the values below. And again, if you need to use pi, use the pi button in your calculator and round your answers to the nearest tenth if necessary. So try number 3. When you come back, we'll do it together. All right, we're back. So we want to find the measure of arc HI, which is this arc here. But we have the corresponding central angle. Remember, this is called a central angle because the vertex of the angle is at the center of the circle. And the corresponding arc of any central angle is defined to have the same measure as its central angle. So the measure of HI, I'm going to say part 1, the measure of HI, the measure of arc HI is 113 degrees. So that was kind of an easy one. Again, if this angle is 113, the central angle, then the corresponding arc measure must be the same degree value. Now we're going to find the measure of angle IKJ. So that's this angle here. And we're going to use the linear pair postulate. We have two adjacent angles, and the non-common side here, or the non-common sides here and here, they're opposite rays, so it's obvious that if you add this angle and this angle, you're going to get 180. They're supplementary angles. So in order to find the measure of angle IKJ, we just subtract 113 from 180, and that will get us 67 degrees. So if you got that answer, good job. All right, try number 4, and when you come back, we'll do it together. All right, we're back. So notice we have this different notation here. That's not the same thing as the measure of an arc. Here, this is asking the measure of an arc. Here, with this notation, it's asking us the actual length of the arc. So we want to know the actual length. Our answer is going to be in centimeters. So the arc length of ln is the central angle divided by 360 times 2 pi r. So what we're doing is we're finding the total circumference, the total distance around the circle. And then we're multiplying by a fraction because we don't want the entire length. We just want this length here. And that fraction is going to be 47 out of 360. And the radius, they tell us, is 5 centimeters. So at this point, I don't really require any more work to be shown. You can just use your calculator. And there's various ways you can do this, but I'm going to take 47 in my calculator, divide it by 360, push the equal button, then times 2 equals, then times the pi button equals, be sure to use the pi button, and then times 5 equals. And the number that I get is 4.10152, so on and so forth, but it says to round off to the nearest tenth. So we're going to erase all of those decimal places. And remember, some of these problems require units. So we found the length of that arc. It's 4.1 centimeters. So if you got that one right, good job. On to number 5. Go ahead and try number 5, and when you come back, we'll do it together. All right, we're back. So we want to find the measure of this arc here. And the way we're going to do that is we're going to find the measure of this central angle using the same formula we did in the previous problem. And then we can use the central angle to find the measure of the arc, because remember, the measure of the central angle is defined to be equal to the measure of the corresponding arc. So we're given the arc length, so we're going to have to use the arc length formula. So the arc length of AB, the arc AB, is equal to the central angle divided by 360 times 2 pi r. And In this case, we actually know what the arc length is. It's 4.5. That's the length from here to here on the arc. The central angle we don't know. We're looking for that. And the radius, of course, is 8 meters. So now we have to solve this algebraic equation for theta. And again, this yellow angle here, that's going to be theta. And then we can use that to find the measure of the corresponding arc, which is what we're looking for, the measure of arc AB. So there's a lot of different ways to solve this, and I don't really require you to show any of that work. You can just enter all this into your calculator and write theta is equal to whatever. The most important thing is that you show the formula that you're using and plug in the numbers. So there's a lot of different ways to do this, but I'm going to show you some of the steps because I don't want you to get confused if I do too much in my calculator. So 8 times 2 is 16, so we have 16 pi. So that's the first step we can do. And again, you don't have to rewrite, you don't have to show every single step here, but I'm going to rewrite to show you the next step. So then we can multiply by 360 in order to get rid of the fraction. Remember, we don't like fractions in equations. We'd like to get rid of the fractions if possible. The 360s cancel out, and you're left with 16 pi theta. I'm going to write 16 pi in front of theta. That's just traditional to write the constant in front of the variable. And at the left side of the equation, we have 360 times 4.5, which is 1,620. And now we're going to divide both sides of that equation by 16 pi, because again we're trying to isolate theta, trying to find theta. Now entering this into your calculator can be it's a source of potential problems. The easiest way to do it is to take 1,620 and then divide by 16 and push the equal button, and you get 101.25. Then divide that number, so divided by, keep that in your calculator and push the divided by button, divided by, and then the pi button, and then equals. Again, there's a lot of different ways to do it, and students will typically do it the wrong way, get the wrong answer, and if that happens, that's okay, but don't get frustrated. Just figure out how to enter it into your calculator correctly. And that's going to be degrees. Now, that's not our answer. We're looking for the measure of arc AB. So if we found theta, then what is the measure of arc AB? Well, actually, it turns out that that is our answer, because the central angle is defined to be the same measure as the arc. So the measure of arc AB is 32.2 degrees. Have you got that one right? Good job. Okay, so again, there's a lot of different ways you can enter that into your calculator, but if you get the wrong answer, don't get frustrated. Just try again until you figure out how to do that. A lot of it depends on what calculator you're using, and so on and so forth. So try problem number 6, and when you come back, we'll do it together. All right, we're back. In this problem, we're going to have to use the perpendicular diameter theorem. And that theorem says that if a diameter or a radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. Again, if a diameter is perpendicular to a chord, then the diameter bisects the chord and its arc. So what that means is that this will be this arc will be congruent to this arc, or not congruent, but they'll have the same measure, and this segment will be congruent to this segment. So the big question is, first of all, do we know that this is a diameter? And the answer is yes, because it's going right through the center of the circle. We were told previously that K is the center of these circles. So we know it's a diameter, but the problem is there's no information here telling us that this diameter is perpendicular to this chord. So what that means is we can't use the perpendicular diameter theorem, and we can't say that this arc is 67, because we know this arc is 67, and the diameter bisects the arc. So the answer to this problem is we really don't have enough information. So that's the answer to that one. Now, if we did know that that diameter were perpendicular, then we could find that this is 67, add these two up, and you get 134. Subtract that from 360, and you'd find this arc, which is what the problem is looking for, or that arc measure. So if you got that one right, good job. On to number 7. For this problem, we need to use the secant tangent segments theorem. It says that if a secant segment and a tangent segment extend from a common point outside of the circle and terminate on the circle, then the square of the tangent length is equal to the product of the secant length and its external length. So I know that seems like a lot to take in, but that just means that 8 squared is equal to 6 times 6 plus x. The square of the tangent length is equal to the product of the total length of the secant segment times the external length. So 8 squared is 64, and using distribution, 6 times 6 is 36, 6 times x is 6x. Subtract 36 from both sides, and that is 28. Divide both sides by 6, and if you reduce, we get 14 over 3. I don't require you to put that in a different form, a mixed number form or a decimal form. You can just leave it like that. But if you want to, you can put it in a different form. It doesn't really matter. So if you got that one right, good job. All right, on to number 8. Go ahead and attempt number 8. And when you come back, we'll do it together. All right, we're back. For this problem, we need to use the perpendicular radius tangent converse theorem. If a line is perpendicular to a radius, and we're talking about the line that contains segment CA, if that yellow line is perpendicular to a radius at the endpoint on the circle, the endpoint being here, the endpoint being here, if that yellow line is perpendicular to the radius, the purple radius, at that orange point, then the line is tangent to the circle. So that yellow line must be a tangent. So we need to figure out if this radius really is perpendicular to the line containing AC. And in order to do that, we're going to use this length, and this length, which is given up here. And we're going to figure out if it satisfies the Pythagorean equation. We're going to use the Pythagorean converse theorem, which says that if a squared plus b squared is equal to c squared, that proves that it's a right triangle, and this is 90 degrees. So if 5 squared plus 4 squared is equal to 2 root 10 squared, then that means that this angle is 90. And if that's 90, it means that the radius is perpendicular to the line containing the segment. And if that's true, then the line must be tangent to the circle. And that's what the problem is asking. They want to know if the line is tangent. So let's do this. 25 plus 16 is equal to, that would just be 2 root 10 times 2 root 10. So 2 times 2 is 4. And root 10 times root 10, remember that just turns into 10. You don't really have to show that work if you don't want to. I'm just trying to give you step by step. 25 plus 16 is 41. So we have 41 is equal to 40. And that is not correct, so we have to put not equal to in all these. And we can just say no. The answer is the line containing AC, segment AC, is not tangent to the circle. So what that means is this angle here, this angle down here is not 90 degrees, so it's not really perpendicular. The line containing AC is not really perpendicular to the radius. So what that means is it doesn't just touch the circle once, it touches it twice, but it's kind of hard to see that in the picture. So if you got that one right, good job. Now it says here, show the calculations you use to determine tangency. That's these calculations here. That's all that I require. And of course you have to actually answer the question. The question is no. AC is not tangent to CB. All right, on to number 9. Go ahead and try number 9, and when you come back, we'll do it together. All right, we're back. We're going to have to use the secant segments theorem, which tells us if we have two secant segments, secant meaning they're not tangent, they don't just touch once, they touch in two places. If we have two secant segments, the total length of one of the segments times the external length is equal to the total length of the other segment times the external length. And that's, of course, if the segments terminate on the actual circle. If they go farther than that, then that theorem doesn't work. So 20 plus 9 is 29. And don't be afraid to use your calculator. We're going to use distribution over here. Remember, you're allowed to use the calculator. So 29 times 9 is 261. And 261 minus 64 is 197. And if we divide that by 8, I'm going to write it in decimal form. You can just write 197 over 8 if you want to as the final answer. I don't really care. So if you got that one right, good job. All right, on to number 10. Go ahead and try number 10, and when you come back, we'll do it together. All right, we're back. We're going to have to use the inscribed angle theorem. That tells you that if you have a circle and an inscribed angle, this is called an inscribed angle because the vertex is on the circle, then the measure of that angle is equal to the measure of the intercepted arc divided by 2. So that's kind of the principle that we're going to be using here. But this problem is going to be particularly easy because this angle here, this 34-degree angle, notice that the endpoints of the points of intersection, I should say, are the same points of intersection of this angle And that green measure is actually what we're looking for. So think about the logic behind this. I mean, if this arc is the same for both angles and they're both inscribed angles, the measure of the angles must be the same. The measure of angle D must be 34 degrees. So this problem was actually pretty easy. Now, you can make that more difficult if you're not quite understanding what is going on there. You can prove that using the inscribed angle theorem, because some students may not be comfortable with that logic. If this angle here is 34 degrees, then by the inscribed angle theorem, this arc must be 2 times that, so that would be 68. And if that arc is 68, then we go backwards to find this angle, because again, that's an inscribed angle touching at those same points of intersection. So if this is 68 degrees, divide it by 2 to go backwards to get to this angle here. And that angle is what we're looking for. That's 34 degrees. So divide by 2, 68 divided by 2 is 34 degrees. So there's really not a lot of work to be shown here. The measure of angle D is equal to 34 degrees, and that's all that I really require. Now, some of the problems on the test, you are going to get a problem like this on the test, but it's not going to be quite that easy. So just be aware of that. Sometimes you'll get easy problems, sometimes they'll be a little more difficult, and sometimes they may be fairly challenging. So if you got that one right, good job. On to number 11. Go on to attempt number 11. When you come back, we'll do it together. All right, we're back. In this problem, we're going to have to use the arc-chord pair congruence theorem. And what that says is if you have two arcs created by chords that are congruent, those chords must also be congruent. And we know that those arcs are congruent because those green tick marks. So the chord lengths have the same, they're the same value. So AB must be equal to 4 millimeters. So that was a pretty easy problem. If you got that one right, good job. Again, some of these are easier than others. Try number 12, and when you come back, we'll do it together. All right, we're back. In this problem, we're going to have to use the chord perpendicular bisector theorem. It says if a chord in a circle is a perpendicular bisector of another chord, so this chord, if that's a perpendicular bisector of this chord, then the first chord must be a diameter of the circle, this chord here. So let me just say that one more time. If a chord in a circle is a perpendicular bisector of another chord, then the first chord must be a diameter of the circle. So we have to figure out if this chord here is a perpendicular bisector of this chord. Now it does bisect the chord because we have 5 feet and 5 feet. It cuts it right in half. And we're also told in those pink letters that this angle here, DEC, the measure is 90 degrees, so that means it's perpendicular. So this chord here is a perpendicular bisector of this chord, proving that BC is a diameter. So the answer is yes. And the explanation, we can just say BC is a perpendicular bisector of the segment AD. So that's all you really need to write for that one. So if you got that answer, good job. All right, try number 13, and when you come back, we'll do it together. Okay, we're back. In this problem, we're going to use the angle vertices outside circles theorem. And I'd like to write a formula, but we'd have to name all these points of intersection. And instead of doing that, I'm just going to say that the measure of angle A is equal to the difference of the arcs that are created by those two secants divided by 2. So that's what the formula tells us. And this works for two tangents. If you have two tangents, the same principle works. The angle is just this arc minus this arc divided by 2. And if you have one secant and one tangent, it works also. So let's say you had one tangent there. Let's say you had a secant here. This angle would be equal to this arc measure minus this arc measure divided by 2. Sorry if that was kind of hard to see. So just realize that there's 3 situations there, but they all use the same type of formula. So multiply both sides by 2 and subtract 40 from both sides. And we found negative x, but we don't want negative x, we want x. So multiply both sides by -1, and we get x is equal to 18 degrees. You can rectangle the whole thing or just rectangle the number. Doesn't really matter. So if you got that answer, good job. On to number 14. It says here, if C and D are points of tangency, that means they hit the circle only once. If C and D are points of tangency, find the following values. So go ahead and try number 14, and when you come back, we'll do it together. All right, we're back. So remember, we learned that theorem that tells us that if a segment or a line is tangent to the circle, and you draw the radius out to that point of tangency, the radius and the segment, they must be perpendicular. So we know that this angle here is 90 degrees, and we know this angle is 90 degrees. And by the way, I forgot to do the first part of the problem. Part 1, BD, that's pretty easy. That's just 3 inches. That was kind of an easy one there. If this radius is 3, then this radius is 3. So anyway, we know that this angle is 90 degrees, and this angle must also be 90 degrees. There's a couple different ways you could do this. You could recognize that this is a kite. It's a quadrilateral, so if you add up all the angles, you get 360 degrees. And how do I know that? Well, because remember, the sum of the angles in a polygon is equal to 180 times the number of sides minus 2. Plug in 4 for n, and you get 360. So we could just add up all these angles, the 4 angles here, 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 and here, and find the missing angle. And then we could just divide that by 2, because we know that if we split this into 2 triangles, this side and this side are congruent, and obviously this side is congruent. And we have another theorem that tells us that if a point outside of a circle is connected with 2 tangents, then those tangents must be congruent. So we can use the SSS theorem to say that those triangles are congruent, and we can just cut this angle in half. There's a lot of different ways to do this problem, but we're looking for the measure of angle ABD, so that's this angle here. We want that angle there. So I'm just going to draw a triangle out here. That's supposed to be a right triangle. Maybe I can draw that a little better. So I just pulled out this triangle here. So again, it's a point of tangency, D that is, so that's a 90-degree angle. And I can just split that 70 degrees in half. So I'll say that's 35 degrees. And we're looking for this angle up here. So using the triangle sum theorem, 35 plus 90 is 125. 125 subtracted from 180 would be 55 degrees. So 180, maybe we can show a little bit of work here. 35 plus 90 is equal to, or actually plus the measure of angle ABD is equal to 180. Do the math on that, and we get the measure of angle ABD is equal to 55 degrees. So if you got that one right, good job. Again, there's many different ways to do that problem. So you can choose whatever method you want. But remember, we have to use that information that we learned about this situation where you have a point outside of the circle extending to two points of tangency. So now let's go to number 15. Try number 15. When you come back, we'll do it together. All right, we're back. We're going to use the tangents from a common point theorem. If that was the same theorem we used over here to say that these lengths are congruent. If tangent segments are drawn from a common point outside a circle, then the segments are congruent. So we have a common point, and tangents are drawn from that point. The segments must be congruent, so that means that x squared must be equal to 25. And we can find x by square rooting both sides. And remember, there's no such thing as a negative length, so we can just say that x is equal to 5. So if you got that one right, good job. All right, on to number 16. Go ahead and try number 16, and when you come back, we'll do it together. Okay, we're back. It says write an equation of the following circle. So remember, the general form of the equation of a circle is the following. And HK is the center. This is the x value of the center point. And this is the y value of the center point. And R is the radius of the circle. Now, we can see the center. If we look over in this the circle here, we can just do some investigation, and we see that if you connect these segments, it seems pretty clear that that's the center of the circle. That's -2, 2. So we have our center, -2, 2. I'm going to label that with a C for center. And we can find R also. R is just the radius, so if you go from the center to a side of the circle, that's obviously 4 units. So R is 4. At this point, all we have to do is just plug in the numbers. So we have x minus the x value of the center plus y minus the y value of the center is equal to the radius squared. So just to be clear, what's happening here, I plugged in that -2, I plugged in this +2, and I plugged in the radius. And maybe I should color these two. Now that's a double negative, so that becomes x plus 2 squared. And there's really not much you can do with the other term. But 4 squared is 16, and that is the equation we're looking for. So if you got that one right, good job. On to number 17. Find an equation of the circle with center -3, -2, and a point located on the circle at 1, 4. So this is going to be the same equation we just used. X minus the x value of the center squared plus y minus the y value of the center squared is equal to r squared. That's the basic form of the equation of a circle. Now, what do we know? We know that the center is -3, -2, so I'm going to notate that with a C, or label it with a C. And we also know that there's a point on the circle. I'm going to call that P, 1, 4. So what do? Well, we plug in the x value of our point, and then we plug in the x value of the center. That's -3. Then we plug in the y value of our point. Whoops. The y value of our point, which is 4. And we subtract the y value of the center. So that's -2. And that's going to help us find r. Once we find r, then we can write the final equation. So 1 minus -3 is 1 plus 3. That's a double negative. And we have a double negative over here. That becomes 4 plus 2. And then we have 4 squared plus 6 squared is equal to r squared. 16 plus 36 is equal to r squared. And then we have, looks like 52 is equal to r squared. Now you don't have to really find r. A lot of students would keep going, square root both sides, but in this particular situation, you don't need to find r. We just need r squared, and then we can plug it back into this equation up here. So now we're ready. We have x minus the x value of the center plus y minus the y value of the center is equal to r squared, which is 52. So I got that r squared from here. And again, I got I don't know if I really need to color these, but I got those numbers from there. So now those are double negatives. So we have x plus 3 squared plus y plus 2 squared is equal to 52. And there you go. So if you got that answer, good job. On to number 18. Go ahead and attempt number 18. And when you come back, we'll do it together. All right, we're back. So for this problem, we're going to use the secant tangent angle theorem. So we have a secant and a tangent, and that theorem tells us that this angle here is, the measure is half the measure of this arc. So it's kind of obvious. So the measure of angle 3 is equal to 140 over 2, which is equal to 70 degrees. Now, if we know the measure of angle 3, we can easily find the measure of angle 2 because this is a linear pair here. We have two angles that are adjacent, and they share a vertex and a common side, but the non-common sides are opposite rays. So obviously these two angles add up to 180. They're supplementary. So we're looking for the measure of angle 2. So the measure of angle 2 is equal to 180 minus 70 degrees, which is 110 degrees. If you got that one right, good job. On to number 19. Go ahead and try number 19, and when you come back, we'll do it together. All right, we're back. Find the measure of arc AB if E is the center of the circle below. So if E is the center of the circle, that means that this is a diameter. And what that means is that the distance, or I should say not the distance, but the measure of the arc from here to here must be 180 degrees. Again, because that's a diameter. It's half of the circle. Half of the circle is 180 degrees. So what we're going to do is we're going to find this arc measure using the inscribed angle theorem, and then we're just going to subtract that from 180 degrees to find the measure of arc AB. So the measure of arc CA, we're going to do that first, is double. And I should write it a little different way. That angle in there, according to the inscribed angle theorem, that angle is equal to the measure of arc CA divided by 2. So multiply both sides by 2, and we get 42 degrees is equal to the measure of arc CA. So again, just to be clear what happened here, we knew that this angle is 21, so the measure of the intercepted arc of that angle must be 2 times that, so 42 degrees. Then we're going to subtract this from 180 to find the measure of arc AB. So that was kind of part 1 of that problem. Part 2 is the measure of arc AB is equal to 180 minus 42. And that would be 138 degrees. So if you got that one right, excellent. All right, go ahead and try problem 20. When you come back, we'll do it together. All right, we're back. In this problem, we're going to need to use the inscribed angle theorem. But to be honest with you, if you really want to, you can just memorize that this angle here is supplementary to the opposite angle in the quadrilateral. So 180 minus 67 is the answer. But that doesn't really explain anything. That just helps you find the answer. If you want an explanation of why that is, and again, I don't really require you to show the explanation, but we're going to use the inscribed angle theorem. So if this angle is 67 degrees, and that means this arc is double that. So that would be 134 degrees. Now, if this is 134 degrees, if you subtract that from 360, that would give you this angle. So 360 minus 134 would be 226. So that arc, that orange arc there is 226. Now notice that that arc corresponds to this angle, which is what we're looking for. So again, use the inscribed angle theorem. That tells you that that orange arc divided by 2 is the corresponding inscribed angle measure. The arc measure divided by 2 is the inscribed angle measure. So 226 divided by 2 is 134. So it always ends up being true that this angle here is supplementary to the opposite angle if this quadrilateral is inscribed in a circle. So the measure of angle S is equal to 180 minus 67, which is equal to 113 degrees. So if you got that one right, excellent. Okay, on to number 21. Go ahead and try number 21. And when you come back, we'll do it together. Okay, if B is the center of the circle below, find DC. So we're going to use the perpendicular diameter theorem. If a diameter or a radius is perpendicular to a chord, see that red box, perpendicular to a chord, Then the radius bisects the chord and its arc. So what that means is this arc measure is equal to this arc measure. We don't really care about that in this problem though. And this segment length must be equal to this segment length. Again, if the radius is perpendicular to the chord, that must be true. This length is equal to this length. So this problem is a little tricky. In fact, it's quite tricky. We're trying to find DC, but how do we find this length or this length? It doesn't seem that the answer really is there. How do we do this? Well, we know that the length of the radius is 10. Now think about that. Do you agree with me that this segment here is 8, right? Do you agree with that? That segment is 8. Do you agree that this segment here is 2? So if you add those segments, you get 10. The radius of the circle is 10. All right? Now, if the radius of the circle is 10, then that means any radius is 10. This radius is 10, this radius is 10, this radius is 10, so on and so forth. But we're interested in this radius, because then we're going to create a right triangle like so. So I'm going to take that right triangle out. And we know that this side is 8, and we just showed that this side is 10, and we need to find CF. And then we can double CF to find CD. So because that's a right triangle, we can use the Pythagorean theorem. 10 squared is equal to 8 squared plus CF squared. So we have 100 is equal to 64 plus CF squared. You don't really need parentheses around the CF because that's not a product, but it's just notation, but probably should just to be safe. And then we have 36 is equal to CF squared, square root both sides. You don't really have to show the square rooting if you don't want to, but I probably should do it so students know exactly what's happening here. And of course, you always write plus or minus, but a length cannot be a negative number, so we can just write positive 6. So CF is equal to 6. Now that we know CF is equal to 6, we can say that CD is equal to 2 times CF, and so our answer is 12. So there you go. If you got that one right, excellent. On to number 22, graph the following equation. So we need to write our basic form of the equation of a circle so we can see what's happening here. So now if we well, I guess I'm just going to rewrite this equation here. There's a lot of different ways that you could do this. Now y squared, I could write that as y minus 0 squared, and I'm just going to do that. I know that's kind of confusing. Whoops, that should be 9. I want to write it as 3 squared. So I changed some things. I changed the 9 to 3 squared, and I changed the y to y minus 0. And think about that. Am I allowed to do that? Is that legal? I mean, y minus 0 is the same thing as y, right? The purple y minus 0 is the same thing as y. And the green 9 is the same thing as 3 squared. So I did that because now it looks more like the basic form. We can start identifying things. So what that means is the center of the circle is h and k, and h is 2 and k is 0. So I'm going to try to label some of this stuff so we can see what's going on. So h went there. I know I probably don't need to do this for a lot of students, but I just want to be clear what's happening here. And we also know that the radius is 3. So I got that from there. And now we have all the information that we need to graph this circle. We have the center and the radius. So the center is 2, 0, that's here. And we know the radius is 3, so we can count out 3, 1, 2, 3. And 1, 2, 3. And 1, 2, 3. And 1, 2, 3 to the left. And then we can just connect the dots. Now, to be honest with you, I really don't care if your circle is perfect. It's hard to draw a perfect circle. And that's not really what this course is about. This is not an art class, so you don't really need to draw a perfect circle. So if your circle looks kind of off, that's not really a big deal. Just try to make it look somewhat like a circle. Now, if you draw something like this, you know, that's not a circle. So don't draw something that looks completely ridiculous. If you draw your circle and it looks completely lopsided like that, you know, that's not. You got to do a little bit better than that. All right, let's go to number 23. Go ahead and try number 23. When you come back, we'll do it together. All right, we're back. For this problem, we're going to need to use the angle vertices inside circles theorem. Again, I'd like to write a formula, but we'd have to name all these points of intersection, and that's kind of a lot to do. So all you need to know is that the measure of this angle is equal to the sum of the intercepted arcs that are created by those segments, or those chords, divided by 2. So what that means is the measure of angle 1 is equal to 132 plus 81 divided by 2. And don't be afraid to use your calculator. Again, a calculator is allowed for this test. So we get 213 over 2. And then when we divide by 2, we get 106. 106.5 degrees. So if you got that answer, good job. On to 24. Go ahead and attempt number 24. And when you come back, we'll do it together. All right, we're back. If the line containing segment AC is tangent to circle B at C, find AC and BC. So if this segment here is tangent to the circle at the point where this radius hits the circle, then we know from the perpendicular radius tangent theorem that this angle here must be a right angle. That must be 90 degrees. So I'm going to pull that triangle out, and I can label that as a 90 degree angle. Probably try to get these angles right. So I'm going to make that a little bigger. Doesn't have to be perfect. So that's a right angle. And this is a 30-degree angle. And if you use the triangle sum theorem, obviously this angle must be 60 degrees. So that's A, that's B, and C. And we're also told, now be aware, we're told that AB is equal to 6. So that side is 6. And actually, maybe I should just label the relations. So remember, if this side is W, then this side is 2W. The hypotenuse is 2W, and this side is W times root 3. That's the 30, 60, 90 degree triangle theorem. But we're told that this side is 6. So we're told that that's equal to 6. So this side must be half of that side. This side must be 3. So AC, that's part 1, AC is equal to 3. And for part 2, the side BC, the side opposite the 60 degree angle, that must be equal to whatever the 30 degree side is equal to, which in this case is 3, times root 3. And so that's it. It's just really a 30, 60, 90 degree triangle problem. So if you got those right, good job. All right, on to the last problem. If M is the center of the circle below, find the measure of angle IMJ. So we're looking for this central angle measure. Says, again, you must use the pi button on your calculator. So don't use 3.14. Use the actual pi button on your calculator. So we're going to use the formula, the area of the sector, IMJ, and I guess I can just write A, capital A for area. I'll just do that. The area of the sector is equal to the total area of the whole circle times a fraction. Now, why is it times a fraction? Well, because we're not trying to find the area of the whole circle. We're just trying to find the area of the yellow part of the circle. But in this problem, we're not really trying to find the area, actually, because they gave us the area. We're trying to find theta, so we're going to plug in numbers that we know and solve for what we don't know. So A is actually 85.52. R is 10. So at this point, you can really do the rest in your calculator. You can find theta by just doing everything in your calculator. But the problem is, the more steps you do in your calculator, the more likely your calculator is going to misinterpret what you're trying to do. So that'll only work if you know exactly how to use your calculator. So I'm going to take it step by step here just to help you. So 10 squared is 100. And then the next thing we want to do is probably get rid of the fraction. Again, you can do this in a different order. It just depends on how you want to do it. So let's multiply both sides by 360. I'm going to use a different color there. And the left side of the equation, 360 times 85.52 is 30,787.2. And the 360s cancel out over here, and I'm left with 100 pi times theta. Now, don't be confused by this, because these symbols, that theta kind of looks like a 0. So now, again, I'm showing a lot of steps here, but you don't have to really show these steps. I don't require you to do that, because this is just basic algebra. So now we're going to divide both sides by 100 pi. So 30,787.2, I'm going to enter divided by 100 equals, and then I'm going to divide by pi, and be sure to use the pi button in your calculator, and then equals. So you should get 97.9987, so on and so forth. If you didn't get that, then that's okay. Don't panic. Don't get too depressed. That just means that you need to learn how to enter the numbers into your calculator. Everybody has to get some practice with that. It depends on if you're using an Android calculator, an iPhone, or a calculator on your computer, or a graphing calculator, or a scientific calculator. They all work differently. Now it says to round to the nearest hundredth, so that's this place here. So I'm going to look to the 8. The 8 tells us to round up, but if we round up, there's nowhere to go, so we have to round this number up, but there's nowhere to go there either, so we have to round this number up, and we end up with 98. So I'm just going to round that all the way to 98 degrees. And I believe that is what we're looking for, the measure of angle IMJ. We should probably notate that, though. So let's show that we found the measure of angle IMJ. I don't really require you to do that, to be honest with you, but just to be clear. So if you got that one right, good job. So that is the test today, the practice test. Be aware that you're going to need to do a practice test for homework. And I know what you're thinking. It's kind of a lot of work to have to do a practice test for homework, but you're going to need to do that test to prepare for the test in the next class. And if you want to take screenshots of everything we did today, please do that, because this is going to help you obviously with your homework, and it's going to help you prepare for the test in the next class. So that's screenshot number 1 and screenshot number 2 and screenshot number 3 and number 4 and number 5 and number 6. But don't go before you get your homework. Here's the practice test that you're going to do for homework. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5 and number 6. Don't go before you get the answers to the practice test. It's not enough for you to just throw some numbers on the page. You have to do this practice test correctly. So be sure and get these answers and check every single answer. Do not just write your answer and then go on to the next problem and assume that you did it correctly. Check every single answer. Make sure that you did the practice test completely correct. So that is the class today. Remember, the practice test is not going to guarantee that you get an A on the test. And be aware that the test, the purpose of it is to prove that you actually know something. That's your chance. In the next class, that you have a chance to actually prove to somebody, most importantly to yourself, that you know something, that you can actually do this math. It's not enough just to look at theorems and postulates and memorize them and think that you know something. The purpose of this course is to learn fluency. And in order to demonstrate that you know fluency, you have to actually be able to do the test in the next class on your own without any help from anybody and get a passing score. So if you want an A on the test, it's not enough just to do the practice test. You're going to have to go back and look at everything that we did in the previous classes and make sure that you know every problem, that you can actually do every problem. So I'll look forward to seeing you in the next class.